So let's say I'm interested in stretching surfaces, like stretching a rubber band, which means it's getting stretched in one direction and it's getting compressed in the other direction. So on the plane, you can represent such matrices by a matrix in SL2R in one direction, and we get compression in the other direction. And you can ask, what are these stretch vectors, possible stretch vectors you can get? Well, it's an easy question here. You can get every real number greater than 1. There is absolutely no constraints. But now, what if I ask what happens to the torus? I also want a similar stretching behavior of the torus, but now this is a closed topological surface, so it's going to be harder. So again, I want one direction getting stretched and the other direction getting shrinked. Lambda and 1 over lambda. And then you quickly realize that once you have a map of the torus, then you can lift it to the universal cover. So it's actually a map of the plane. And then in order for that map to descend down to the torus, you see that integral points must map to integral points. So actually, these maps can only arise from matrices in SL2Z. So suddenly, the topology of the surface induces some really, really strong restrictions on the possible stretch vectors you can have. Because here, lambda is going to be a root. It's an eigenvalue of such a matrix. So it's a root of some x squared plus kx plus 1, such a polynomial. In particular, it's an algebraic integer, an algebraic unit, and its degree is 2. Now you can go further and ask, okay, what if you take an even more complicated surface? You take a genus 2 surface and ask, okay, how can I get such a stretching on the genus 2 surface? And it turns out that there's no way to do such a thing, because for specifying the directions, we need these foliations. And the foliation would mean a non-vanishing line field, which is only possible if the Euler characteristic is 0. But what you can do is, instead of such foliations, you can introduce singular foliations that have certain singularities. And you can take pairs of such foliations, and you still get some stretching behavior. Are 2, 3, 4, and 6. 5 is not possible. Anything larger than 6 is not possible. Again, the topology of the surface tells something about the stretching. Degree is the stretch vector is always an algebraic integer, so it has some minimal polynomial. It's the degree of the minimal polynomial. So it was Thurston's very important discovery that these stretching maps play actually a really important role in the study of surface homeomorphisms. So what he showed is that, so let's define the mapping class group first. So mapping class group of a surface is the set of orientation preserving homeomorphisms up to isotopy. So what Thurston showed is every element in the mapping class group is either finite order, which is really simple, reducible, which I'm not going to explain now, and the third type is Pseudo-Anosov, which is precisely this type. And moreover, most of the mapping classes fall into the third category. So the generic type is really, if you take a random surface homeomorphism, it will take this form. this.
The action of this mapping class on the homology is on the eigenvalues of that sp2gz matrix related to these.
Yeah, sometimes, yes. If these foliations are special, if they are orientable in some ways, then those eigenvalues, one of the eigenvalues will be the stretch factor. In that case, these foliations are represented homologically. But if you have an odd singularity, then they are not. So it's there's some connection. I mean, 3. Here there is 3 prongs coming out from the singularity. You can have 4-pronged or 5-pronged or 6-pronged. Odd number, yes. Right. So so we have this lambda associated to any mapping class. It's actually invariant of the mapping class, so it's invariant up to isotopy. So some of the connections of Pseudo-Anosov mapping classes to other areas. You can take a surface, cross it with an interval, and construct a mapping torus once you have a surface homomorphism by gluing the top and the bottom. And this is a hyperbolic 3-manifold if and only if the mapping class is Pseudo-Anosov. Moreover, the volume of the manifold is related to the stretch factor. Another connection to a different area is the Teichmüller and modular spaces of surfaces, which is just the set of Riemannian metrics or a set of algebraic curves, and this is the set of set of Mord hyperbolic metrics on the surface, and any mapping class is acting on the Teichmüller space, and the action is analogous to an action of a hyperbolic isometry of the hyperbolic plane that acts by a translation along an axis. And this translation distance is precisely log lambda in the Teichmüller metric. And since the Teichmüller space is covering the moduli space, Pseudo-Anosov maps also correspond to closed geodesics in the moduli space. And the length of the closed geodesics are also related to the stretch factor. Right, so some of the questions you can ask about stretch factors. What is the minimal stretch factor on SG? There is always a minimum which is realized. So this minimum is always greater than 1, and it's realized as Pseudo-Anosov map. And the answer is only known for g equals 1, which is trivial, and 2. So even for g equals 3, we don't know what's the minimal stretch factor.
Easier if you punctures,
Once punctured torus is still easy, but twice punctured torus, it's more. The more punctures you have, the more difficult it gets. Maybe the twice punctured torus is known. Right. Question a little bit simpler by considering lambda min plus. So what is lambda min plus? Like I said, sometimes these foliations that you get are orientable in some way, and in that nicer property, in that nicer situation, the stretch factor is going to be related to homology. So here more is known but not much more. Only for 1, 2, 3, 4, 5, 7, and 8. So it also happens that if the genus is divisible by 6, for instance, then the whole situation is a little bit different than other genus. Another question that you can ask is, well, I was telling you that here on the torus the degree must be 2. Here the degree can be a little bit more complicated. So we can see that as the genus increases, algebraically more complicated stretch factors can appear. So what are the possible degrees for lambda? And Thurston showed an upper bound that the degree is almost at most 6g minus 6. In both of these cases, well, it's when g is at least 2. So here it's realized. But for instance, 5, you can get 5. And this is ruled out by another criterion. Long showed that the degree is at most 3g minus 3 if the degree is odd. So these two conditions, so these are all the numbers. So all the numbers, we can get all the numbers here that are subject to these two conditions. But what the question is, what about in general? Can we get everything subject to these conditions, or maybe there are more conditions? And recently I've shown that at least for even degrees, you can get everything. So every even degrees between 2 and 6g minus 6 occur. And the odd degree case is still open. All right. I think I would just say, since this is a really specialized topic, I would just mention a few other areas I'm interested in, since it's the introductory talk. I'm also interested in, like Alex Wright was talking about it, translation surfaces. And billiards. The way this topic is related to translation surfaces is once you have the two transverse foliations, Euclidean metric, a singular Euclidean metric, it's singular because of the singularities on the surface. So for every Pseudo-Anosov map, you get some translation surface. Also, fibration of 3 manifolds. So related to this example, if you have a 3 manifold, then by work of Thurston and Kurt McMullen, it turns out that the possible fibrations of a 3 manifold over the circle has actually a very nice structure, and so you can look at what kind of Pseudo-Anosov maps can arise from a fibration of a single 3 manifold over the circle. And braid groups, for instance, the faithfulness question of the Burrao representation of 4 braids. Yeah, I'm not going into details. Thank you.
Thank you very much.